Let's kick this skill off by talking about something that we have yet to really address, which is how exactly we are sending our network traffic through these uplinks between the fabric interconnects and the chassis themselves. And furthermore, since the chassis are connected via these I/O modules, the I/O modules are basically fabric extenders. And the same principles will apply to the I/O modules, in other words, to the chassis connectivity, as they will to a fabric extender. For example, if we decide to go with rack mount servers instead of blade servers, then we might have a bunch of FEXs in our environment, and those FEXs connect down to our servers. And so it's important to understand that the same principles will apply. And so in this video, we're going to see exactly how the network flows between, again, our servers and our fabric interconnects. Let's jump in. So as a quick review, when we have our fabric interconnects in our environment and we're ready to connect these down to a chassis, the chassis needs some kind of way of connecting up via networking. And the way we do that is by deploying these I/O modules. The I/O modules slide into the back of the chassis. And as we've mentioned a few different times, these are architecturally speaking a Nexus fabric extender. Keeping in mind that these upstream devices, these fabric interconnects, are effectively Nexus devices. I'll put this in quotes because they're not literally Nexus devices, but architecturally speaking, they might as well be. And so they have the ability to be the parent device for fabric extenders, in other words, our I/O modules. One of the advantages of fabric extenders is the streamlined management process. We don't have to treat each one of these FEXs in a data center as an individual management point. FEXs were originally designed because we had dozens, if not hundreds, in some large data centers of top-of-rack switches. And because we kept scaling out our servers, we need more and more of these top-of-rack switches, and this was an IP address that I had to log into and manage and maintain a configuration. And Cisco said, well, hey, instead of that, let's deploy fabric extenders. And fabric extenders do what they sound like they would do. They extend the fabric of a parent switch. And so at that point, we keep management up here, and we don't have to worry about managing the fabric extender. Well, that benefit is also realized in UCS, because we know that we have UCS Manager that we're configuring and using to manage the UCS infrastructure, but this UCS Manager is primarily pushing configuration down to these two devices, and the fabric interconnects themselves are pushing configuration down to the I/O modules. And the best part is that that's all happening without us having to intervene with anything. And this is just architecturally how Cisco designed it, and this really ends up enabling us to configure everything through UCS Manager. Now these I/O modules, they can be 10 gig or they could be 40 gig. And furthermore, they can have 4 ports or they can have 8 ports. So let's say we're ready to connect our I/O modules up to our fabric interconnects. Well, our network brains might be inclined to say, all right, we're going to create a full mesh, something like this. But this is a big no-no inside the UCS architecture, because really what we need is we need to create individual uplinks between an I/O module and a parent fabric interconnect. And the reason for this is because we want to create distinct fabrics. We're going to connect down to a virtual interface card, in other words, a VIC, and these I/O modules are going to have several connections into the VICs potentially. And what we see here is that the VIC has 2 different loop-free networking paths that it can choose to send its traffic up. Now when we create our VNICs down here, we have talked about before how the VNIC itself gets assigned to a particular fabric. Let's say the VNIC on the left is assigned to fabric A, the VNIC on the right is assigned to fabric B. Well, now we can see the distinct fabric paths that we have that give us loop-free access into and out of the UCS architecture. So the focus of this conversation is going to be right here, the connectivity between the fabric interconnects and the I/O modules. So let's talk about that a little bit. First of all, we can support 1, 2, 4, or 8 connections to the I/O module. We don't want to support 3, for example, or 5 or 7. Any of those configurations would be considered invalid. Furthermore, we can configure pinning or we can configure port channels. Let's start with the concept of pinning. What exactly is this all about? We're probably familiar with the idea of pinning. We understand, we've talked about before, that we have these virtual Ethernet interfaces on the fabric interconnects, and those get hard pinned to an uplink. So if I have, let's say, 4 different uplinks here, remember, I'm not running spanning tree on this fabric interconnect. And on a switch, these would be individual loops because they're connecting up to another switch. However, because each virtual Ethernet interface on a fabric interconnect is connecting up to a distinct uplink, well, we create a loop-free environment via pinning. Well, we can use that same technology on these links between the I/O modules and the fabric interconnects. In fact, if we do nothing else but just simply connect up the uplinks, this is going to be the default behavior. Cisco UCS by default is going to use pinning instead of a port channel on those links. And yet, just like our fabric interconnect uplinks, these are all active. Every single one of these connections, whether it's 2, 4, 8, or I suppose 1, either way, they are all active in forwarding traffic. This is the magic of pinning. It's why we can get away with lots of active connections without having to rely on spanning tree to block the loops. So the way this works is every single server, more at this point we're talking about a physical UCS server, not a service profile. Every physical server in the environment or maybe I should say inside the chassis, is going to be pinned to a specific I/O module uplink. And this is going to happen on the A side, and it's going to happen on the B side. So looking back at the drawing here, what we have is we have a physical server. Let's just call this our blade. The green rectangle is housing the VIC, it's housing the VNIX and all that. But at some point, we have to run this on physical hardware, as we've joked about in the past. And so this blade is the physical hardware. We have connections internally up to each I/O module. But then what happens when we get to these connections? Well, that's going to be determined by two different factors. First of all, the server ID. What server number is it inside the chassis? And second of all, how many uplinks do we actually have? Let's walk through this. Let's say we have two different uplinks. How exactly do the servers get pinned in this scenario? Well, if we have two uplinks, then servers 1, 3, 5, and 7 are all going to get pinned out port number 1. So that would be the odds, which means the evens, 2, 4, 6, and 8, these are all getting pinned out link number 2. So just to draw this out, let's say we have an I/O module and we have made two connections up to our fabric interconnects. Well, the way we're going to do this is as traffic comes into the I/O module, if it came from, let's say, server 1, well, that's going to get pinned out port 1. And so server 1 gets pinned out this interface, so do, by the way, servers 3, 5, and 7, and now we're starting to see how this comes together. Because if we get traffic into the I/O module and it's sourced from server number 4, let's say, it's going to get pinned out the right side, which is where we have servers 2, 4, 6, and 8 pinned. So let's look at a couple other examples. What if we have 4 uplinks, which is what we have in the drawing here, by the way? Well, in this case, we're going to pair up our servers. So servers 1 and 5 go out link number 1. 2 and 6 go out link number 2. 3 and 7 go out link number 3. And 4 and 8, those go out link number 4. So as we can see, UCS is always going to load balance this as best as possible. With the 2 uplink scenario, we see that we are putting 4 servers on one link and 4 servers on the other link. But with 4 uplinks, now we see that we're only putting a pair of servers on each link. Now you can probably guess what an 8 uplink scenario looks like, and you're probably correct. Server 1 goes out link 1, server 2 goes out link 2, all the way down until server 8 goes out link 8. At this point, every server gets its own dedicated uplink from an I/O module. Now the question you may ask is, all right, so this is great and all, but what happens if one of these uplinks were to go down? Our drawing on the right, for example, what happens if the link on the left goes down to these 4 servers? Well, when we're using pinning, these 4 servers lose their access to the fabric. Keeping in mind, by the way, that this is only one I/O module. This is I/O module A. And so over here, we do have I/O module B that also has a connection down to the same server. So if this is server 1, let's say, server 1 did just lose its access to fabric interconnect A. And the reason for that is its pinned uplink went down. However, fortunately for us, we have a second fabric interconnect in this. And so chances are we have the same number of uplinks to the I/O module on the right. And so we still have a path out to the rest of the network via fabric interconnect B. So if you're not a big fan of this scenario, then you might want to consider port channeling. Port channeling is certainly an option. We can simply bundle all of these connections together. So over here on the left, I would bundle these 4 connections together. And on the right side, I would bundle those 4 connections. And now we have a single logical connection. At this point, all of the servers, servers 1 through 8, are going to get pinned to the port channel. This means that if a link were to go down for any reason, well, we just lost a physical link, but we still have the logical link. So the physical might be down, but guess what? Because the logical is up, we can continue to send traffic for all 8 servers across that logical connection. This is a huge boost from a resiliency perspective. However, we do actually see a downside to this configuration, and that would be control. Keeping in mind that when we were pinning traffic, as we described over here, we knew exactly how much bandwidth every single server was guaranteed to get. In fact, if we were to embrace the 8 uplink methodology, we could ensure that every single server is guaranteed the full amount of bandwidth of a single connection. And so that is one reason why we might consider deploying pinning into our environment. But I will say that from experience, the resiliency is usually enough that we want to configure port channels in our UCS environment. However, that said, we always want to make sure that we're doing exactly what's best for our environment. And so when we run our analysis, when we're deploying a UCS into our infrastructure, we can make the decision between pinning and port channels. And so as we see here, the default setting in UCS is actually to use pinning on the uplinks between our I/O modules and our fabric interconnects. And that can come with some control. However, we also saw that if a server's pinned uplink were to go down for any reason, then we lose access to the fabric on that side. And so that lack of resiliency might lead us to want to deploy port channels. Port channels are absolutely an option for us. We can configure that in UCS Manager and tell it, hey, we want port channels down to our chassis. And that does give us the added resiliency of losing a link and all of our servers stay online. But at the same time, we do have to make sure that bandwidth allocation is all taken care of in the QoS world, because the last thing we want is one server taking all of the bandwidth of that link. and making it so that the other servers are just contending for attention and contending for more bandwidth. I hope this has been informative for you. I'd like to thank you for viewing.